Welcome to A-Level Chemistry. Today we are going to solve the February-March 2021 paper 12, and this is the MCQ paper. And while we do this, I'll show you some techniques that you can use during the exams to get a good score on this paper. Now, one of the main things that you should remember is that reading the question is probably the most important thing. When I used to practice for this paper, I used to make the mistake of reading the questions too quickly, and then I'd miss out some important detail and I'd make some silly mistake. So if you can minimize the number of silly mistakes you make, you can actually get a very good score on this paper. So starting from the first question, the table shows the number of protons, neutrons and electrons in 4 different particles W, X, Y and Z. Which pair represents the atoms of 2 isotopes of the same element? Now, you have 4 options always, and sometimes we look at one option and we think that's correct and we won't go through the other options, but I would suggest against that, because if you can rule out if you can go through each and every single option and then you can make sure that only one of them is correct, then you'll be more confident in your answers and the level of accuracy will also be higher. So let's start from the first option, W and Y. So the number of protons are 32 in each, and therefore these can be isotopes, because the definition of an isotope is that they have the same number of protons but different number of neutrons, and also the same number of electrons. So if you look at the number of neutrons in these, it's 40 and 42, they are different, and the number of electrons is also the same. So A is a good candidate for this answer, but let's not stop there. If you look at W and Z, they have different number of protons, 32 and 34, and therefore this can definitely not be an answer. If you look at X and Y, they have the same number of protons, they have a different number of neutrons, but they have different numbers of electrons as well. And therefore we cannot have X and Y as the answer. Then we look at X and Z. We have 32 protons, 34 protons. No, this cannot be an answer because different number of protons, not isotopes. So we know that A has to be the correct answer in this case. Then question 2. Where in the periodic table is the element that has an outer electron shell arrangement of 4s2, 4p3? So first we look at the principal quantum number. It is 4. So the principal quantum number is 4, and therefore if we look at the options, we can rule out A and C, and we know that it has to be one of B and D, because the element has to be in period 4, because the principal quantum number is 4. Now group 13 and group 15. Now if you remember nitrogen, this electron shell arrangement looks very similar to that of nitrogen, and therefore we know that it has to be something in group 15, because only group 15 elements will have this electronic configuration, and therefore the answer has to be D. Then we move on to question 3, and according to the examiner reports, this was one of the hard questions in this paper, and that is true because it is quite involved. So let's get on with it. Substance Q is a hydrocarbon. When 1.00 grams of Q is completely burned, 3.22 grams of carbon dioxide is produced. What could be the identity of Q? So let's note down the masses first. Let's underline these important details that they have given, and substance Q is a hydrocarbon, which is also an important detail. Now the thing with this question is that we have to go through each and every option, because just by looking at it we will not get anything in our brains. So let's look at cyclohexane first. We know that the formula of cyclohexane is C6H11. Always write the formula for organic compounds, the molecular formula, because it does help you get somewhere with the answer. Now let's write a balanced equation for this combustion reaction. So C6H11 plus something O2 gives CO2 plus something H2O. So we know that there are 6 carbon atoms here, so there should be 6 carbon atoms on both sides. But to balance it, I'll put a 2 here and I'll put a 12 there, just for balancing. I'll put an 11 here because there have to be 22 hydrogens on each side. And then this will give us 17.5 moles of O2 in the balanced equation. You can write whole numbers, just multiply the whole thing by 2, that doesn't matter. So this is for option A. And now let's do this for all other options as well, and then we'll see where to go with that. So cyclopentane is C5H10. Remember, it's an alkane, but it's cyclic, so it has to have the same molecular formula as the alkene, pentene, so C5H10. Ethene will be C2H4, and then pentane will be C5H12. So let's write down the balanced equations for all of these. C5H10 plus 7.5O2 gives, you can see if the balancing is correct later on, plus 5H2O. C, it is C2H4 plus 3O2 gives 2CO2 plus 2H2O. Then D, it's C5H12 plus 8O2 gives 5CO2 plus 6H2O. Now, we have these balanced equations, and I think all of them are balanced if I've done it correctly. Now, we know that there are 3.22 grams of carbon dioxide that are produced, so we can calculate the number of moles. We know that N, which is the number of moles, is equal to M over Mr, which is equal to 3.22 over 12 plus 16 into 2, the mass of carbon plus the mass of two oxygens, and this is equal to 0.0732 moles. So if we have 0.032 moles of 0.732 moles of carbon dioxide, then if you look at the balanced equations, we'll have the ratios of the hydrocarbon to that of CO2. So for A, 2 moles of C6H11, which is cyclohexene, produce 12 moles of CO2. And this means that there's a 1:6 ratio between the hydrocarbon and CO2. And if we calculate the number of moles of cyclohexene, which is N is equal to 1.00 over 12 into 6 plus 11, and this is 0.0120. If we multiply this by 6, we'll get somewhere closer to 0.0732. Not exactly, but somewhere close. So A is a good candidate for the answer. For cyclopentane, we have N is equal to 1.00 over 12 into 5 plus 10 is equal to 0.0143. And this will, if you look at the second equation, which is for B, 1 mole of C5H10 gives us 5 moles of CO2. So if we multiply 0.0143 by 5, we will reach somewhere close to 0.0732, but not as close as we reached in A. So this is not a better answer than A, and therefore we can cross it out. If we do the same for ethene, we get N is equal to 1.00 over 12 into 2 plus 4. And this will be equal to, sorry, I'm running a bit out of space. That's always a problem with the MCQ paper, 0.0357. And if you look at the equation for this, 1 mole of C2H4 gives 2 moles of CO2. You multiply 0.0357 by 2, again, you get somewhere close to 0.0732, but not as close as A again. And therefore, C is also not the correct answer. The last option, we have N is equal to 1.00 over 12 into 5 plus 12, which is equal to 0.0139. And from the last equation, we can see that 1 mole of C5H12 gives 5 moles of CO2. And therefore, if we multiply 0.0139 by 5, we should get 0.0732, but we don't get that. We get something similar again, but not as close as A. And therefore, we can cross this out, and therefore, we know that A is the correct answer here. And you can see how much there was to do in this question, and that's why it was one of the hardest questions in that paper, but it's not always like this. Now we go to the next question, question 4. Originally, chemists thought that indium oxide had the formula INO. By experiment, they showed that 4.8 grams of indium combined with 1.0 grams of oxygen to produce 5.8 grams of indium oxide. The AR of oxygen was known to be 16. Which value for the AR of indium is calculated using these data? So we can first write an equation for, always write the balanced equation when it's these mathsy questions. If you don't get the balanced equation, you won't get the correct answer. So always first get the balanced equation. So 2In plus O2 gives 2INO. This seems pretty balanced. And we know from this equation that the number of moles of indium should be equal to the number of moles of indium oxide, because they're in a 1:1 ratio. So when 4.8 grams of indium combined with 1.0 grams of oxygen, we get 5.8 grams of indium oxide. And what we do in this question is that first we need to figure out which one is the limiting reagent. So we don't know the mass of indium, and therefore I don't think they would expect us to get the limiting reagent. But if we knew the mass of indium, then we would be expected to see which one is the limiting reagent. Now we know that because we know that indium and indium oxide are in a 1:1 ratio, we know that the number of moles will be the same. So the number of moles of indium will be 4.8 over x, where we have taken x to be the mass of indium, and this will be equal to 5.8 over x plus 16, which is the mass of indium oxide. So 4.8 over x, which is moles of indium, is equal to 5.8 over x plus 16, which is the moles of indium oxide. And from this we can get we can get an expression in linear in x, and that can be used to calculate x. So we get 4.8x plus 76.8 is equal to 5.8x, and this gives x is equal to 76.8, which is and the closest to this value is 77 here, so that's what we will go with. In which substance are the only intermolecular forces temporary dipole induced dipole attractions? So temporary dipole induced dipole attractions, this should ring a bell that it's only for non-polar molecules. So we look at option A, hydrogen chloride. Very polar cannot be the answer. It will either have hydrogen bonds, less likely, but more likely permanent dipole attractions. Methanol, we know OH groups, hydrogen bonds, cannot be the answer. Octane. Now for hydrocarbons, the thing is that the electronegativity of carbon and hydrogen is very similar, and therefore hydrocarbons are always non-polar. So octane is a good candidate for this question. Water, H2O, hydrogen bonds cannot be the answer, and therefore we are left only with octane. A solution contains 0.25 grams of sulfur dioxide in 1 dm cube of water. Which volume of sulfur dioxide measured at 50 degrees Celsius and a pressure of 10 to the power 5 pascals must be added to 1 dm cube of water to produce this solution? So in this question, we know that sulfur dioxide is SO2, and we always assume these gases to be ideal gases. Now I know that sulfur dioxide obviously doesn't look to be something like an ideal gas. It's very far from what noble gases, which are the closest to ideal gases, are. But we always assume, because they have not said anything else, we always assume it's an ideal gas. So we start with the ideal gas equation, which is PV is equal to nRT, and then N is therefore equal to PV over RT. So we have P, we have V, we have to find V, sorry, and we have R, and we know R is equal to 8.314, and we know T is 50 degrees Celsius. Remember, T has to be in Kelvin, however. So first we calculate the number of moles. We know that we have 0.25 grams of sulfur dioxide dissolved in 1 dm cube of water. So the mass is enough. The 1 dm cube of water is not any essential information. So N is equal to 0.25 over 32.1, which is the mass of sulfur, plus 16 into 2, which is twice the mass of oxygen atoms. And this is equal to 0.00390 moles. So this is the number of moles of sulfur dioxide. Now we have to calculate V. So we make V the subject. We know nRT over P is equal to V, because we know PV is equal to nRT, and we have N, we have R, we have T, and we have P as well. So we just plug in the values and we get the answer. So 0.00390 into 8.314 into 50 plus 273. Remember, temperature in Kelvin, not in Celsius in this equation, over the pressure, which is 1 into 10 power 5, and this gives a volume of 0.000105 meter cube. Remember, if you put everything in SI units, you will also get the volume in SI units, which is in meter cube. And the options, if you see, are all in centimeter cube. So you multiply this by 10 to the power of 6, which will give you 105 centimeter cube. And that's option D here. Then question 7. An experiment was performed to determine the enthalpy of combustion of ethanol. And they've given a diagram which we don't need, I think, but always good to know what's happening. The data collected are shown. So they've given you the mass of water, mass of ethanol burned, temperature rise, molar mass of ethanol, specific heat capacity of water. So these are the values that are given to you. Which expression can be used to calculate the enthalpy of combustion of ethanol in kilojoule per mole? So remember, Q is equal to minus mc delta T, where m is the mass of water. Remember, it's the temperature of water that is rising. It is the energy of burning ethanol that is being transferred to the water, and therefore the m that we will use will be the mass of the water and not the mass of the ethanol. So this is a very important thing to remember. So Q is equal to minus mc delta T. We know that m is equal to W, so minus W. C is equal to 4.2, so into 4.2. And delta T is equal to Y degree Celsius, so Y. Kelvin degree Celsius does not matter because the change in temperature will be the same in either case. So Y. And now we have Q, but we don't want Q. We need the enthalpy of combustion, which is delta H in kilojoule per mole. So delta H will be equal to Q, which is the energy transferred, over the number of moles of ethanol. And we know that the number of moles of ethanol is the molar mass of ethanol, the mass of ethanol divided by the molar mass of ethanol. So this will be equal to Q divided by X over Z. X is the mass of ethanol burned, Z is the molar mass of ethanol, and this is equal to minus 4.2 W YZ over X joule per mole. Remember, we have still not converted the value to kilojoules, so this is only in joule per mole. And then we divide this by 1000 to get it in kilojoules per mole. So we get minus 4.2 WYZ over 1000 X kilojoule per mole. And therefore the answer is A. Now we move on to the next one. VO2Cl reacts with NaI under acidic conditions. 2VO2Cl plus 2H2SO4 plus 2NaI gives VOCl2 plus VOSO4 plus I2 plus Na2SO4 plus 2H2O. The oxidation state of chlorine is -1 in VO2Cl. So before doing anything, we'll note it down over here. And in VOCl2 as well. So we noted, so there are two chlorines here, so total will be -2, -1 plus -1, which is -2. Which row about this reaction is correct? So we want to know what happens to the oxidation state of vanadium and what happens to the oxidation state of iodine, because that's what the options say. So let's look at VO2Cl first. So VO2Cl, we know the chlorine is -1. We know oxygen is -2, but there are two oxygens, so -2 into 2, which is -4. And we know that VO2Cl is a neutral species, so V has to be +5. So V is in +5 oxidation state. VOCl2, then we have Cl -1, two of them, so -2. Oxygen is -2 as well. The vanadium is therefore +4 because VOCl2 is a neutral species, so we get V +4. So the vanadium has gone from +5 to +4, which means it has reduced, and therefore only C or D will be the answer. We already know A and B cannot be the answer. Now we will have a look at iodine. So this was for vanadium. Now we'll have a look at what happens to iodine. NaI, we know that Na will be +1 always, so I will be -1, and therefore I is in the -1 oxidation state. And I2, which is the elemental form of iodine, will be in 0 oxidation state because it's a molecule, not an ion. It's a molecule with itself. Oxidation state has to be 0. So the oxidation state of iodine goes from -1 to 0, and therefore it has increased, and the iodine is oxidized. So the correct answer is option C. Question 9. In which reaction is water behaving as a Bronsted-Lowry base? Now, before answering this question, we recall the definition of a Bronsted-Lowry base. This base accepts a proton. So we know that. Let's go with this. Now the first option, H2O plus Na gives NaOH plus half H2, and in this the water is behaving as an acid, not a base, because it is donating a proton. The H2O is converted to OH negative, it is donating a proton, so this cannot be the answer. Second option, H2O plus H3PO4 gives H3O plus H2PO4 negative. Very clearly we can see the water is accepting a proton. It is acting as a Bronsted-Lowry base. This might be the correct answer, but we want to make sure. Option C, H2O going again to hydroxide ions. It's donating a proton. Cannot be the answer. Ammonia plus this transition metal salt giving NH4 plus. Again, the fact that the NH3 is being protonated means that water is donating a proton and a hydroxide is produced. Cannot be the answer. So we know the correct option is B. A large excess of marble chips is reacted with 25 centimeter cube of 1.0 mole per dm cube hydrochloric acid at 40 degrees Celsius. Again, before we go in delve into the question, marble chips, calcium carbonate, hydrochloric acid, So we know what's happening here. Carbonate is reacting with an acid. We know what to expect. We don't know yet what the question is asking for yet, but at least we know what is going on in this reaction, which is very important, as then you'll be ready to answer any sort of questions. How is the result different when the reaction is repeated with 60 centimeter cube of 0.5 mole per dm cube? Now, remember, the starting of the question says marble chips are in excess. We really don't have to worry about them anymore. And we have different amounts of, different volumes and concentrations of hydrochloric acid being used at 40 degrees Celsius. Temperature is also constant. So let's read the options. The reaction is faster and more of the products are made when the reaction is complete. Now, the temperature is the same. The concentration is lower, and therefore A cannot be the correct answer, because the concentration is lower, so the reaction will be slower. The reaction is faster and less of the products are made when the reaction is complete. Again, the reaction has to be slower, so B cannot be the answer because the concentration is lower. Option C, the reaction is slower and more of the products are made when the reaction is complete. So the reaction is slower, we know that, but the amount of products, let's see how many moles of hydrochloric acid are being used. So in the first case, we have 25 over 1000 into 1. Remember, centimeter cube needs to be converted to dm cube, and this is 0.025 moles. In the second case, we have 60 over 1000 into 0.5, which is equal to 0.030 moles. So the amount of HCl is larger. Marble chips are in excess. So if more HCl is being used, more products will form, and therefore option C has to be the correct answer. Then we move on to question 11. The Boltzmann distribution curve for a gaseous mixture of ethene and hydrogen is shown. Nickel is an effective catalyst for the reaction that occurs. How does the diagram appear if the same reaction mixture is at a higher temperature? Now, before reading the options, we need to recall what happens when the temperature is increased. When the temperature is increased, the Boltzmann distribution curve becomes flatter, its peak shifts to the right, and we see something like this. So now that we know what is happening, let's read the options. The curve is unchanged. That is not true. We just showed that the curve moves to the right and its peak becomes smaller. The values of both activation energy catalyzed and the activation energy uncatalyzed decrease. No, that is not true, because the activation energy is independent of temperature. The values of both activation energy catalyzed and uncatalyzed increase. Again, activation energy is independent of temperature. Last option, values of both activation energy catalyzed and uncatalyzed remain the same, and that is the correct answer. Which observations are made when a sample of silicon chloride is added to a beaker of water? Again, leave everything else, write the equation. We need to know what is going on in the reaction always. So this gives us SiO2 plus 4HCl. Balanced equation, done. Now let's read the options. No visible changes observed. That is not true, because we get a solid precipitate SiO2. We get steamy fumes of HCl, and then The second option is steamy fumes and a precipitate observed. Yes, that's what we just said. The appearance of a precipitate is the only observation. No, we also see steamy fumes. The appearance of steamy fumes is the only observation. No, we also see a precipitate. So option B is the correct answer. Which row is correct? Statement, they've given a statement and they've given the reason. So what we'll do first is we'll only read through the statements and then we will look at the reasons, so that we can at least, if one statement is wrong, then we know that that option cannot be correct. So statement 1, the first ionization energy of phosphorus is greater than that of magnesium. That is correct, because as we move across a period, ionization energy increases. The melting point of phosphorus is greater than that of magnesium. This is not correct, because magnesium is a metal, metallic bonds, phosphorus is a non-metal, covalent bonds, and we know that metallic bonding is very strong, melting points of metals are high, and therefore B is wrong. The statement is wrong, so we know B cannot be the answer. The atomic radius of phosphorus is smaller than that of magnesium. Yes, because as we move across a period, the atomic radius decreases because of the greater pull of the nucleus. The electrical conductivity of phosphorus is smaller than that of magnesium. This is undoubtedly correct, because magnesium is a metal, phosphorus is a non-metal, metals are better conductors of electricity. Now we'll move on to the reasons. We will not read the reason for statement for B, because we know that the statement is wrong. So option A, electron is lost from 3p orbital in both cases. Now this is wrong, because magnesium's valence orbital is an s orbital. For phosphorus it's a p orbital, and therefore the reason is wrong. Then option C, phosphorus has greater nuclear charge than magnesium. That is correct, because as we move across a period, nuclear charge increases. Both statement and reason are correct. Option C is a good candidate. The electrical the bonding changes from ionic in magnesium to covalent in phosphorus. This is a correct statement, but it is not the reason for the electrical conductivity difference, because the reason for the electrical conductivity difference is the free electrons in magnesium, and there are no free electrons in phosphorus. And also I just realized the reason is wrong, because the bonding in magnesium is not ionic, it is metallic, and therefore this reason is wrong. So we know the correct answer has to be C. Then question 14. Which row correctly describes one property of barium and one property of barium oxide? So barium is a group 2 metal, and now let's read the options. Observation: when barium metal is added to water, a few gas bubbles form at the metal surface. No, that's not true, because barium is quite down in the group 2, and therefore we will expect a more vigorous reaction than this. So A is wrong. We have a similar observation in B, so B is also wrong. So we know that it has to be one of C or D. Rapid effervescence is seen, yes, because barium is quite down in group 2, will be expected to react very vigorously with water. And then the pH of a solution obtained when a spatula measure of BaO is added to 100 centimeter cube of water. So barium hydroxide is very alkaline, because it's very soluble in water, so barium is very soluble in water. Barium oxide is very soluble in water, and it forms barium hydroxide. And because barium hydroxide is so soluble, it is very alkaline, and because it is very alkaline, we would expect its pH to be very high. 8 is close to neutral, so I wouldn't expect that to happen. 13, more alkaline. Yes, that's more reasonable. The correct answer is D. Now we look at question 15. An anhydrous white salt, Z, so white salt underline, anhydrous also underline, is heated strongly for 30 minutes. A mixture of gases is given off. A mixture of gases is given off. Now let's stop here and read the options. Barium carbonate, barium nitrate, magnesium carbonate, magnesium nitrate. When you decompose a carbonate, the only gas you obtain is carbon dioxide. When you decompose a nitrate, the two gases you obtain are nitrogen dioxide and oxygen. So you know that because the question says a mixture of gases is given off, it doesn't say a single gas is given off, it has to be a nitrate. So we've already narrowed it down to B and D. Now let's read the rest of the question. The solid remaining in the test tube is then dissolved in a small volume of dilute hydrochloric acid. The addition of a few drops of dilute sulfuric acid to the test tube causes a white precipitate to form. Now, for the MCQ paper and also for paper 2, you need to remember the qualitative analysis sheet that you get in paper 3, which is the practical paper. And if you go there, you will see that Ba2 plus gives a white precipitate with sulfate ions, and therefore it has to be barium nitrate and not magnesium nitrate. Chlorine gas is reacted with aqueous sodium hydroxide. The oxidation number of chlorine changes from 0 to -1 and also from 0 to +1. Under which conditions does the reaction occur, and what is the color of the solid silver salt with chlorine in the oxidation state? Now we remember, in the oxidation state -1. Now we remember that when we react with cold dilute alkali, we get, I'm not balancing this equation, but we need to know the products, plus H2O, I think. Yeah, I think it's H2O. Oh, no, I don't remember what it was, sorry. So let's leave it there because we don't really need it. NaCl is in the -1 oxidation state, and the Cl is in the -1 oxidation state. In NaClO, the Na is in +1, oxygen is in -2, and Cl also has to be in +1. So the question says that the oxidation state goes from 0 to -1, 0 to +1. So yes, the cold dilute alkali is a reasonable answer. So it cannot be C and D, because if you remember, when in hot concentrated alkali, we get NaClO3 alongside NaCl. So we get NaClO3, which is, we get +1, and then 3 oxygens, -2 into 3, -6, and that's +5. So sorry, the Cl is in +5 oxidation state in this one, and therefore this cannot be the correct answer. It's not C, it's not D. Color of silver salt. When you add silver nitrate, or any silver salt for that matter, you'll get AgCl. This is always a white precipitate. AgBr is a cream precipitate. AgI is a yellow precipitate. So AgCl is white, and that's what we get. So it has to be A. Now, let's go to question 17. When concentrated sulfuric acid reacts with sodium iodide, the products include sulfur, iodine, hydrogen sulfide, and sulfur dioxide. Now, I'm not going to write a balanced equation here because because it's a very tedious task to do. What I'll do is I'll just go from H2SO4 to H2S, S0 and SO2. S0 is basically elemental sulfur in zero oxidation state, because they have given us the products. We write down the products and we write down the reactant. And from the sodium iodide, we get I2. So these are the two things that we are getting. Now, which statement is correct? Hydrogen sulfide is the product of a reduction reaction. So let's look at this first equation involving the H2SO4. So in this one, the SO4 is a 2 negative ion. 4 oxygens will give 8 negative, and to give an ion of 2 negative, we'll need 6 plus for sulfur. In H2S, 2 plus from the two hydrogens, and therefore the sulfur has to be 2 negative. So oxidation state goes from +6 to -2, and therefore it's a reduction reaction. This statement is correct, but we'll read the other ones as well. Now, iodide ions are stronger oxidizing agents than sulfate ions, and this option is not correct, because iodide ions are strong reducing agents, because they're they're not very electronegative, so they don't want electrons much themselves. They are ready to give them up. Sulfur atoms from the sulfuric acid are both oxidized and reduced. No, that's wrong, because only reduction happens, because if you look at SO2, the 2 oxygens -4, sulfur +4. So overall, sulfur is going from +6 to -2 in H2S, +6 to 0 in elemental sulfur, and +6 to +4 in SO2. So only reduction of sulfur is happening. This option is wrong as well. Has to be A. Then question 18. NO2CO and unburnt hydrocarbons are present in the exhaust gases of internal combustion engines. When catalytic converters are used to remove these compounds, from the exhaust gases, redox reactions occur. So from our knowledge, what we can do is we see these compounds, we know what happens to them because we've learnt about this. So NO goes to N2, NO2 goes to N2 as well, carbon monoxide goes to CO2, and the unburnt hydrocarbons go to CO2 and H2O. So if you look, it's only asking about oxidation and reduction. So let's start from NO. We know that oxygen is -2, N has to be +2, and in N2 it is 0. So the NO is definitely reduced, which means the answer can only be C or D. We've already narrowed it down. Then we look at NO2, and it goes to N2 and 2 oxygens -4, so +4 for the nitrogen. The +4 goes to 0 in N2, and therefore it is also reduced, which is in both options, so we didn't really have to do that. Then carbon monoxide, we know that oxygen is -2, carbon is +2 here, but in carbon dioxide, the total is -4 from the 2 oxygens, and therefore from the carbon it is +4. So it goes from +2 in carbon monoxide to +4 in carbon dioxide. Oxidation is happening, and therefore C is the correct answer. And if we look at unburnt hydrocarbons, if we probably do the same method, we will get oxidation as well. So the correct answer is C. Methylamine CH3NH2 has similar chemical properties to ammonia NH3. Methylamine reacts with hydrogen chloride to form a white crystalline salt, methylammonium chloride. So they've given us an equation here. A sample of methylammonium chloride is reacted with aqueous sodium hydroxide. Now remember, when we react an ammonium salt such as NH4Cl with a base like NaOH, we get NaCl, which is a salt, plus NH3, which is ammonia, plus H2O. Remember this concept, and we can apply the same concept to methylammonium chloride. The only thing that is changing, that instead of using ammonium chloride, NH4Cl, we are using methylammonium chloride, CH3NH3Cl. So just like ammonium chloride gives us ammonia, methylammonium chloride should give us methylamine, and the other products will be the same, and that's what we see in option D. Now we'll move on to question 20. The structure of citric acid and isocitric acid are shown. So they've given us the structural formula. How many chiral center does each acid possess? So we'll start with citric acid, and we'll start with this carbon. This is not a chiral center because it has a double bond. This one is not a chiral center because bonded to 2 hydrogens. This one is also not a chiral center because it is bonded to one CH2CO2H group here and another CH2CO2H group here. 2 of the same groups cannot be a chiral center. Again, the carboxylic acid carbon is never a chiral center. Then we get to the bottom row. CH2, not a chiral center. C of the carboxylic acid, not a chiral center. So the citric acid has 0 chiral centers. So we narrow down the answer to C and D. Then we look at isocitric acid. Again, starting from the top row, from the right. Carboxylic acid carbon, not a chiral center. CH2 carbon, not a chiral center. This carbon is a chiral center because it is attached to one H, one CO2H, one CHOH CO2H, and one CH2CO2H, all different groups. So this is a chiral center. However, the carboxylic acid is not a chiral center. The bottom row carbon, this is also a chiral center because it is attached to 4 different groups, as you can see. And then the carboxylic acid carbon, not a chiral center. So you have 2 chiral centers in isocitric acid, and therefore the correct option is D. And then how many tertiary alcohols have the molecular formula C6H14O? Let's draw them out in the space given over here. So C6H14O, one of the isomers we will get, it has to be a tertiary alcohol, remember. They've given it has to be tertiary alcohol with 6 carbons. So what we'll do is, we'll first build up the tertiary carbon framework. Yeah. Now we have 4 carbons already, we need to add 2 more, and the isomers will basically result from where we add the 2 more. So we can add the 2 more on this carbon atom. This is one isomer, and then we build the framework again. And then we can add 1 carbon here, and we can add another carbon here. So this is another isomer. Instead of adding them in a straight chain, we branch this one. Then we can have another one, which is again make the framework of the tertiary alcohol. And then we can add one carbon here and one carbon here, and that's 6 carbons again, another isomer, and that's the only isomer. We are not worried about any chiral centers because, as you can see, none of these will have any chiral centers. So that is 3 isomers, and therefore C. The diagram shows the structure of a bromo compound that may be formed by the reaction of bromine with a hydrocarbon. Okay, which row is correct? So bromine with a hydrocarbon. The hydrocarbon can be an alkane and an alkene, but we will rule out alkene here because if you see the molecule, this molecule over here, we have one bromine on this one and one bromine on this one, and these 2 carbons which the bromine is on cannot be directly double bonded because there is another carbon between them. So this cannot be an addition reaction, and therefore we will rule out the first 2 options. Then we look at the rest 2, which is substitution reaction. The substitution cannot be nucleophilic because we are using Br2 bromine as one of the reactants, and we only always get a single substitution, but here we have a double substitution, and therefore it cannot be a nucleophilic substitution, and it has to be therefore a free radical substitution. Now we move on to question 23. Part of the structure of strobilurine is shown. R and R prime are inert groups. Strobilurine is warmed with aqueous sulfuric acid producing compound X. Compound X is then treated with hydrogen in the presence of a nickel catalyst producing compound Y. Now before we look at the options, let's see what is happening here. Warmed with aqueous sulfuric acid producing compound X. You see aqueous sulfuric acid, you see an ester group, you know it's a hydrolysis reaction. We will get a carboxylic acid and an alcohol. So and then compound X is then treated, which means the remaining carboxylic acid from the molecule is then treated with hydrogen in the presence of a nickel catalyst producing compound Y. This is a hydrogenation reaction which happens at the alkene groups, as you know, and therefore it has to be a carboxylic acid, a saturated carboxylic acid with basically no carbon-carbon double bonds. So option A is a good candidate for that. Option B, we don't have a carboxylic acid, not a good candidate. Option C, we don't have a carboxylic acid, not a good candidate. Remember, the alcohol group here cannot be here because if you see the ester group, the carbonyl group is on this carbon, so therefore the alcohol group will be on this carbon. We'll get CH3OH as the alcohol, not this group as the alcohol. So C is wrong. D, we have the carboxylic acid, but then we have these random hydroxyl groups on this, which basically is an addition reaction on the alkene, but we know this is not addition of OH. We know it's an addition of hydrogens only, so D is wrong. Correct answer is A. Which compound produces a ketone when refluxed with an acidified solution of potassium dichromate? Now again, we know ketone oxidation because potassium dichromate has to be a secondary alcohol, a 2-degree alcohol. So which one of these are 2-degree alcohols? Pentan 1-ol, you see the 1-ol, and you know it's not a 3-degree alcohol. You can draw it out and see for yourself. 1-degree alcohols give aldehydes, not ketones, on oxidation. 2-methyl-butan 1-ol, again another primary alcohol. Draw it out, you will see it as primary. 2-methyl-butan 2-ol, it's a tertiary alcohol. Let's draw this one. CH3, CH2, COH, CH3 whole twice. This carbon is bonded to 3 other carbons, 2 from the methyl groups, these ones, and 1 from the CH2. Tertiary alcohols, they do not get oxidized. C cannot be the answer. So D is the only one left. 3-methyl-butan 2-ol. Let's convince ourselves this is correct. So CH3 whole twice, CH, CH, OH, CH3. This carbon bonded to this carbon and this carbon. So 2 other carbons, 2-degree alcohol, correct answer. Question 25. Dibromopentanes can undergo double elimination reactions to produce hydrocarbons. 2NaOH plus C5H10Br2 gives C5H8 plus 2NaBr plus 2H2O. which isomer produces only one hydrocarbon product? So we know that if only one hydrocarbon is to be produced, we cannot have any we need to have we cannot have any cis-trans isomers, and therefore because it's an elimination reaction, so you get alkenes can be cis or trans, but if it's only one hydrocarbon, cannot have cis-trans. So 1,5-dibromopentane is BrCCC. I'm not drawing the hydrogens because we don't need them. Br, and this will undergo elimination to give CCC. Now, because we have two terminal carbons with alkene groups, we can't have any cis-trans isomers because both of them will have two identical groups. So A is a good candidate because we'll get only one hydrocarbon, which is this one. And then let's look at the other options. 1,4-dibromopentane, BrCCC, and then we have the Br on this one this time, and this eliminates to give CCC, and this will have cis-trans isomers around this alkene group, and therefore we'll have two products. Not possible. D is wrong. And if we do the same thing for C, we'll get similar analyses, and therefore A has to be the correct option. The diagram shows the formation of compound Y from compound X in a chemical reaction. R1 and R2 are alkyl groups. So it's X plus HCN in the presence of a KCN catalyst gives us this compound, which has an OH group and a CN group. Automatically this should ring a bell. It's a nucleophilic addition reaction. So we know that it has to be either of C or D. And then because R1 and R2 are both alkyl groups, X has to be a ketone and not an aldehyde, because in aldehyde there is one hydrogen bonded to the carbonyl and one R group, but in a ketone there are two R groups bonded to the carbonyl. So it's C. In question 27, in this question you can assume that that one hydrogen and three hydrogen have the same chemical properties, which is basically hydrogen and tritium, and a sample of ethanol contains only one isotope of hydrogen, which is the H1, and it is reduced to compound Z, C2H6O, in a nucleophilic addition reaction using NaBH4. All the hydrogen atoms in the NaBH4 are the 3H isotope. Okay, so CH3CHO plus NaBH4 gives us this compound. We know NaBH4 is a reducing agent. So let's see what's happening. CH3CO, this is the aldehyde. This gets reduced to CH3. And remember, this is H1 because they've said that this only isotope of hydrogen in the ethanol is H1. So this is H1. This undergoes reduction with NaBH4, which has only H3 to give CH3COH. This will be H3 because the NaBH4 is H3, H1 which was already present in ethanol, and H3 which has been added to the ethanol. Now compound Z is then oxidized back to ethanol and water, and which statement about the final mixture of products is correct? Both ethanol and water contain tritium atoms. That will be the correct option, I suppose, because you will eliminate this group, which will give you H2O, in which one hydrogen will be 1 and the other hydrogen will be 3, will be tritium, and will leave you with CH3COH3, and therefore both of them have H3, and therefore this is the correct answer. Let's look at the other ones. Ethanol is the only product containing tritium atoms. No, that is wrong, because as we see, water also has them. Neither ethanol nor water contains tritium atoms. Completely wrong. Both have them. Water is the only product containing tritium atoms. Again, no, both of them have tritium atoms. A has to be the correct answer. Ethane dioic acid has the formula HO2C CO2H. What is the formula of aluminium ethane dioate? Aluminium is a metal. Ethane dioic acid is an acid, and this will give a salt. Now there are two acid groups. So the conjugate base of this acid will be this one, it has an overall charge of -2. So our anion has an overall charge of -2. Our cation has an overall charge of 3 plus. So we have O2C CO2 overall 2 negative. So you can use the cross method of charges and you'll get Al2 and then this group 3 times, and that's option D. Which reaction gives butanoic acid as one of its products? Acid hydrolysis of butyl ethanoate? No, because butyl will give butanol. Ethanoate will give ethanoic acid. So butanoic acid, no. Alkaline hydrolysis of butyl ethanoate, again butanol, ethanoic acid, and not even ethanoic acid. We'll get sodium ethanoate. For example, if the alkali is NaOH, we never get ethanoic acid. We always get the carboxylate ions in alkaline hydrolysis. Again, wrong. Acid hydrolysis of ethyl butanoate, ethanol and butanoic acid, that's what we want. This seems like the correct answer. Alkaline hydrolysis of ethyl butanoate, ethanol plus butanoate ions, because again alkaline hydrolysis does not give the acid because the acid will react with the alkali. So it will give us butanoate ions, not butanoic acid, which is not what we want, and therefore option C is the correct answer. Question 30. When reactant X is treated with a suitable reagent, products Y and Z are formed. Infrared spectra of X, Y, and Z are shown. So before looking at the options, let's look at what's happening in the infrared spectra and decipher them. We have a sharp peak at around 3000 and we have nothing interesting in the spectrum, and these are for CH, remember, from your data book. Product Y, we have a peak which is sharp, but it's not strong enough. So again, CH. Then we have a peak at about 1700 with sharp peak, strong peak, CO. Then product Z, very broad peak around 3000, OH, sharp and strong peak, CO. And that's what we have. Now let's look at the options. So X we know is only CH bonds, and therefore it cannot be option D because propyl propanoate cannot be the first one, and it cannot. And now we'll move forward with the other ones. So X can be either of the things in A, B, and C. Now let's look at Y. Y we know has CH and CO, so it has to be a carbonyl compound. So we have narrowed our options to A and B because it cannot be ethanoic acid, does not have an OH group. Remove C. And then we go to product Z. We know product Z has OH, it has CO, has to be a carboxylic acid, and therefore it has to be option B. So you just narrow it down like that and find the correct answer. Then we go to section B. I don't know if the format is still the same with these rules for the answers, but let's just do it. A sample of 17.15 mole of HI is in dynamic equilibrium with 2.27 moles of H2 and 2.84 moles of I2 in a volume of 1 meter cube at 764 Kelvin and 141 kPa. The two equilibrium constants Kc and Kp can be calculated for this mixture. And this is a cruel question because it has a lot involved in this, Kc and Kp both. Which statements about the equilibrium constants for this mixture are correct? Neither Kc nor Kp has any units. That is true because you have Hi squared on the top and H2I2 in the bottom. So overall you have the same number of units on top and bottom, and therefore they will cancel out and they won't have any units. Kc is equal to 45.6. We'll have to calculate this. So it will be 17.15 squared over 2.27 into 2.84, which is equal to 45.6. This is correct. Kc greater than Kp. We will have to calculate Kp, and which is why I said this is a cruel question. So the total number of moles, we just add them up and we get 22.26. And then we calculate the mole fractions. So for Hi, the mole fraction will be 17.15 over 22.26, which is 0.77. For H2, it will be 2.27 over 22.26, which is 0.10. And for I2, it will be 2.84 over 22.26, which is equal to 0.13. So we know the pressure is 141 kPa, and the volume is 1 meter cube. So we can, because the units are cancelling out on both top and bottom, we don't really have to multiply by the total pressure. We don't have to multiply the mole fraction by the total pressure, because the total pressure on top and bottom will eventually cancel out. So we can just use the mole fractions for Kp, and therefore Kp is equal to 0.77 squared over 0.10 into 0.13, which is equal to 46.5, and we know Kc is 45.6, and this option says Kc greater than Kp, which is wrong, and therefore the answer has to be B. An energy cycle for the combustion of methane is shown. So this is the energy cycle. Which expressions can be used to calculate the energy delta Hz? So this is delta Hz. Delta HF naught CH4 plus delta HC CH4. So we know that it's a Hess cycle. So this root will be the same as this root. So delta HF CH4 plus delta HC CH4 will give delta Hz. That's correct. And then the second option is delta H naught C plus 2 delta H naught C H2. And if you look at this is basically combustion of carbon plus twice the combustion of hydrogen, and we have 1 carbon, 2 hydrogens, which is why they've multiplied by 2. So it's a very reasonable answer, and that's why this will be correct as well. Delta H naught C carbon monoxide plus 2 delta H naught C H2. Now, although this will be correct, this one is wrong, because from going to carbon monoxide, we also have to consider the enthalpy of combustion. We cannot do it just for carbon monoxide, and therefore option 3 is wrong. So again, B is the answer. Then we go to question 33. Many gases do not obey the general gas equation at high pressures. Why is this? This is all bookwork, so if you learn the content well, you'll be able to get this. At higher pressures, the molecules have more energy. This is wrong, because the energy does not change with pressure. Option 2, at higher pressures, the volume of the molecules is a larger proportion of the total volume. That's correct, because if you increase pressure, the gas molecules will come together, and therefore the total volume of gas decreases, but the volume of individual molecules is the same. So at high pressure, volume of molecules will be a larger proportion of the total volumes. And then option 3, at higher pressures, the molecules experience greater intermolecular forces. That's correct, because if they are closer together, there'll be greater intermolecular forces. So the correct answer is C. Which species can accept a lone pair of electrons to form a coordinate, which is a dative covalent bond? So BF3, this is correct, because B is electron deficient. It has 3 electrons, and it has 3 electrons itself. It forms bonds with 3 fluorines, so it gets 6 more. It has total 6 electrons now, 1 coming from each fluorine, and it can take 2 more to complete its octet. And then H plus has no electrons. It can accept a lone pair, so obviously it can accept a dative bond. And then carbon has 4 electrons. Each hydrogen gives 1 electron, and there's a positive charge on the molecule, so you subtract 1 electron, and therefore it can accept a lone pair, because you have 4 electrons from the carbon, 3 from 3 hydrogens, minus 1 because of the positive charge, total 6 electrons. To complete octet, it will accept a lone pair, so 3 is also correct. Correct answer is A. A sample containing X moles of Al2Cl6 is dissolved in water to give solution W. In order to precipitate all of the aluminium from its hydroxide, Y mole of sodium hydroxide are required. More of the alkali is added to redissolve the precipitate, giving solution Z. The initial pH of solution W is below 7. That is correct, because as Al2Cl6 dissolves in water, we get HCl, which is acidic. Y is equal to 3x. Now this is wrong, because let's write an equation. X Al2Cl6, because we have X moles, plus 6x NaOH. You'll know why I'm using 6x here. Gives 2x AlOH whole thrice plus 6x NaCl. This is the only way you can balance this equation. So y should be equal to 6x and not 3x. So this is wrong. Z contains X moles of aluminium. No, Z will contain 2X moles of aluminium because we have Al2. X moles of Al2 is 2X moles of aluminium. So correct answer is D. Nitrogen dioxide gas is produced when petrol is burnt in car engines. Which acids are made in the atmosphere as the result of this release of nitrogen dioxide into the air? H2SO3? No, this is not made because of nitrogen dioxide. H2SO4? Yes, this is made because of nitrogen dioxide, because remember, it catalyzes the formation of acid rain. HNO3, again, NO2 dissolves in water to give HNO3. So the correct answer is C. Question 37. In which reactions is the major product formed by a nucleophilic substitution reaction? Bromoethane plus potassium cyanide and ethanol? Yes, the cyanide ions will replace the bromide ions, and therefore we will have a nucleophilic substitution. Bromoethane plus ethanol under reduced pressure? Yes, because the NH2 group will replace the bromide group, and again a nucleophilic substitution reaction. Bromoethane plus hot concentrated sodium hydroxide and ethanol? No, this is elimination. Remember, these conditions are for elimination, so this is wrong. Answer will be B. An excess of P reacts with Q in the presence of concentrated sulfuric acid to form R. Effervescence is seen when a piece of sodium is added to pure R, which means that so structure of P is shown. So P reacts with Q in the presence of concentrated sulfuric acid. Concentrated sulfuric acid, they've given the structure of P. So Q can either be a carboxylic acid or an alcohol, or probably both, because if it's a carboxylic acid, it will react with the OH group. If it's an alcohol, it will react with the carboxylic acid group, and in both cases they will give different esters. Effervescence is seen when a piece of sodium is added to pure R. So that means R contains a carboxylic acid group or an alcohol group, because remember, sodium reacts with both. So which organic compounds could be Q? So if Q is a carboxylic acid, it will react with the alcohol group of P, and it will leave the carboxylic acid group of P, which will react with the sodium. So this is correct. Then this option 2 is an alcohol. It will react with the carboxylic acid group of P. It will leave the alcohol group of P, and the alcohol group of P the remaining alcohol group will react with sodium. So this is also correct. 3 is a ketone. The ketone will not react either with the alcohol or with the carboxylic acid in the presence of sulfuric acid. So this is the wrong answer, and therefore the correct answer is B. Second last question. 2 carbonyl compounds have the molecular formula C3H6O. Which reagents give different observations with these 2 compounds? So carbonyl compounds can be aldehyde or ketones. Acidified aqueous potassium manganate, yes, this will give different observations because it will oxidize the aldehyde, but it will not oxidize the ketone. Felling's reagent, it will react with the aldehyde, not with the ketone, so this as well. Alkaline aqueous iodine. So alkaline aqueous iodine, remember, it only reacts with CH3CO or CH3CHOH groups. So the ketone will be CH3COCH3. The aldehyde will be CH3CH2CHO. The ketone has the CH3CO group, the aldehyde does not. So it will react with the aldehyde but not with the ketone, and therefore it will only give it will give different observations with the 2 compounds, and hence the correct answer will be A. The last question. An organic compound T does not fizz when aqueous sodium carbonate is added to it. So that means it is not a carboxylic acid, because it does only carboxylic acid groups react with sodium carbonate. Compound T contains 27.6% by mass of oxygen. Okay, so what could be the identity of T? So we can already rule out option 3 because it's an acid, and we know T is not an acid. Then propanol. Propanol is CH3, CH2, CHO, and it has a total mass of 12 into 3 plus 6 plus 16, which is 58. Percentage of oxygen is equal to 16 over 58 into 100, which is 27.6%, which is what we need, and therefore option 1 is the correct answer. Is one of the correct answers probably. Ethyl butanoate, CH3, CH2, CH2, CO2 CH2 CH3 gives it's a total mass of 106. You can calculate that. Percentage of oxygen is equal to 16 into 2 over 116 into 100, which will also equal to 27.6%, and therefore this is also correct. So the correct answer is B. So that was the Feb-March 2021 paper 12. I hope the answers made sense, and if you have any doubts, leave them in the comment section. I won't be able to reply to the emails anymore. I'm sorry about that, but I will try to answer your questions in the comment section. And thank you for watching. Bye-bye.